Hello everyone, let's start this lecture. So in the previous lecture, we talked about microstrip antenna, and we thought of microstrip antenna as essentially an aperture antenna. So we had two radiating slots on the two sides of the patch, and through that slot, this microstrip antenna will radiate. And it's an aperture antenna because we have a certain electric field distribution over the aperture of the antenna, and then through this electric field distribution we get to our radiation and desired radiation, in fact. So now in this lecture we're going to look at one of other types of aperture antennas, which is called open-ended waveguide antenna. So I'm close to an open-ended waveguide antenna, which in this particular one is used for performing field measurements. So the application of this, it has several applications. One of them is in the area of near field antenna measurements, which is not related to our course, but just wanted to essentially show this antenna. So as most of you know, a waveguide is essentially a hollow tube. In this case, this is your hollow tube. So as opposed to a standard transmission line that we studied when we had two different uh, metallic, for example, wires, or in the case of microstrip antenna, we had the ground plane and then we had a strip that was our second conductor. This is essentially one piece of conductor, which is in this case a hollow tube with rectangular cross section, and essentially it guides electromagnetic wave toward its length. So the electromagnetic wave from the back is fed to this system by a coaxial cable, and then electromagnetic waves travels in this structure, which is open-ended, which is a waveguide antenna. So this waveguide, it can guide the wave, and then if you leave the end of it open, it essentially becomes an open-ended waveguide, because when the wave is traveling through this waveguide, electric field has a distribution. So if you look at my fingers, for example, this is similar to distribution here, that the electric field, let's say, let's assume we know the fundamental mode. In the fundamental mode of that is a maximum at the center, and it gradually goes to zero, which is the electric field over the aperture. Remember that the electric field over the aperture is in this way, and it gradually gets smaller when you go to the two walls of the open-ended waveguide. And the reason is on the two walls you have metal, and you know that the tangential electric field over the metal based on boundary condition needs to go to zero. So you have maximum here, and it gradually go to zero on the wall. So that's why I'm saying it's very similar to this distribution, and that you start from maximum at the center and gradually go to zero. And so this is a waveguide that we have, and this waveguide works above a certain frequency. So for example, you may think of it as a high pass filter. Below certain frequency, it does not guide. After a certain frequency, which we call it cutoff frequency, it guides. And when it guides different modes. So that means different field distribution within the waveguide. So the first one that it guides, we call it fundamental mode. And what I'm discussing in these lectures is essentially related to the fundamental mode after the cutoff and before the second mode come into existence. So that would be just the territory of fundamental mode, which would be our focus here. So as I mentioned, as this is working above a certain frequency. For example, if you want to work in a lower frequency, you need to change your waveguide. For example, this waveguide that I have here is ideal for X-band, which is approximately between 8 and 12 gigahertz. Now, if you want to be working at lower frequency, then you need to change your waveguide, and that's the smaller the frequency. Remember, the wavelength becomes bigger. Everything is with respect to wavelength, so the waveguide becomes larger. So now I'm going to show you a waveguide which is for lower frequency, and as if you compare it with that, for the same field distribution over the aperture of the two waveguides, so exactly the same thing, maximum here and going to zero here, and the same thing with that, which is our fundamental mode. The size of this, the physical size of this is of course larger, because this is operating in lower frequency. And by the way, here you can also see the feeding point of this. So you can bring the energy using coaxial cable to the waveguide, and then it's going to travel. And now we keep the end of it open, and it in fact creates our open-ended waveguide antenna. So if I'm not mistaken, in the video related to lab 3 part 1, I'm talking about the radiation. We're measuring the radiation pattern of this open-ended waveguide antenna. So now perhaps let's go to the whiteboard and start talking about our open-ended waveguide antenna and how we can find this radiation pattern using equation. Just before going, let me emphasize again that as you see this waveguide, it has a narrow wall and it has a wide wall. So in the fundamental mode, the electric field is along the narrow wall. So this is going to be the polarization. So it's going to be along the narrow wall. This is your electric field. So the wave is traveling, let's say, toward you. So this is the electric field, and then we're going to talk about magnetic field too. But for one thing, remember, if this is your electric field is perpendicular to the direction of propagation. So this is your electric field. This is the direction of propagation. Therefore, electric field is perpendicular. And that's why we call it transverse electric. That means electric field is perpendicular to the direction of propagation, transverse electric. So that's so I think that's let's go to the whiteboard and discuss more materials on the whiteboard. Thank you. Okay, let's continue our discussion regarding this open-ended waveguide antenna on the whiteboard. So what I mentioned is that waveguide is essentially a metallic hollow tube. So this is essentially a waveguide. So here I have a metallic wall, here I have a metallic wall, and all the walls are metallic wall. And in fact, electromagnetic wave is gonna be guided through the waveguide. So my purpose here is not to teach waveguide. You're going to learn about waveguides in other courses, but we're going to use it as an antenna. So one thing I've mentioned is here is that, so when you have two wires transmission line and essentially two conductor, you have the chance to have transverse electromagnetic wave. So that essentially means your electric field and magnetic field, for example, this one, are both perpendicular to the direction of wave propagation. So transverse means perpendicular, and this is for electric field, this is for magnetic field. So you can have the transverse electromagnetic mode. So, or perhaps in the case of microstrip line, you're going to have quasi TEM. So, but when you go to the waveguide, you cannot have TEM, and essentially this does not have two different conductors. It's just one piece of conductor which is hollow. Let's talk a little bit about that, although it's not directly related to our course, but I think it's good to discuss it a little bit here. So imagine this is the cross section of your waveguide. So now I want to assume that waveguide supports TEM and see what's going to happen if we make this assumption. So you see, if this is, for example, assume a certain electric field. So the electric field that I was assuming when I was talking that in the anechoic chamber was an electric field like that I said you have maximum electric field here and it gradually goes to zero. So if this is your electric field and this waveguide guides the energy toward you, you immediately see that E is perpendicular to the direction of propagation. So this is fine. So, but now the question is, can H also becomes, can H also have, can also be perpendicular to the direction of propagation in this structure? Now, for me to show you, imagine that this is a set of electric fields. So this is a waveguide. So this is a waveguide that we are using in the videos related to measurements for performing measurement. So this is my waveguide. So over the aperture of the waveguide, assume that I have these electric fields. And of course, we are talking about time varying electromagnetic fields. So I have a bunch of electric fields that as a function of time, they have variation, but the electric fields are going in this direction. Now, electric fields are like that and are perpendicular to the direction of propagation. But when they do that, remember that because electric fields are varying, I'm going to have a curl of H around them. So based on this equations in Maxwell's equation, you have curl of H. So let me just write this curl of E. You have minus di B di T. Curl of H, you get J plus di D di T. And remember, if I'm in air, free space, I don't have a J, so let's not consider that for now. Just say curl of H is equal to di D di T. And you also know that D is epsilon E, so curl of H becomes epsilon naught di E di T. So let's focus on that. We usually consider it in the phasor domain, which convert di T to j omega, so it becomes j omega epsilon naught E. So that's for the derivation in the time domain. But this is better for now to discuss in time domain. So that essentially says if you have a bunch of E that's varying with respect to time, you're going to have a curl of H around them. So if I have this electric field here like that, that's changing with respect to time, I'm going to have a curl of H around them. Now look at this curl of H that I'm using this black pen to show you. This is the curl of H. And immediately, look at this point. Immediately you see I have an H toward you, which was the direction of propagation. So that's, let's have some coordinates here. So let's assume this is X, this is Y, and then Z would be toward you. Now, if this is my E, H is going to have Z component right now, and then it's also going to have X component, and then it's going to come back with that. So the H that I'm going to have, then my E is EY, and my H becomes HZ and HX. And the direction of propagation, of course, is Z. It's toward you. Now, if you look at that, only electric field is perpendicular to the direction of propagation because H has a component in the direction of Z. That's why if you just maybe think about it more, you see that there is no way that you can have transverse electromagnetic. You might choose it in a different way that H has no component in the direction of propagation, then E will have some component. So that's why the modes, and that means field distribution, the modes that this waveguide support is either TE or TM. So TE means electric component is perpendicular like that, and TM means magnetic field is perpendicular to the direction of propagation. Therefore, E will have a Z component. So TE and TM, and then these TE and TM can have different forms, different distributions, and we consider, for example, subscript M and N to say these are our different modes. But the mode that is relevant to our course is the fundamental mode, the first mode that can be created in this waveguide. So after the cutoff frequency, the first mode that can be created, and that mode is TE10, and it's exactly this electric field that I've plotted here. It's TE10. The reason to have one here is that if you look at in the X direction, you see that you have one peak here. So you have one peak, and that's the reason for having this one. And if you move along Y direction, you see no change. So that's the reason for having 0 here. It's actually uniform if you move along Y direction. So this TE10, it's my fundamental mode for this waveguide. So if I write electric field, for example, in this case, I can write my electric field is going to be, for example, E naught cos pi x divided by A in the direction of y hat. Now, what is a small a? That's essentially this dimension. So this is a. Therefore, here I have a divided by 2. Here I have minus a divided by 2. And the vertical dimension is b. So if you look at here, if you substitute x equal a divided by 2, that means you are on this wall, then your E becomes essentially 0, because that's, you're going to end up with cos of 90, which is 0. So your E becomes 0. That's very good, because you know that over a PEC or metal, E tangential needs to be 0. And remember, E in the y-hat direction is tangential to this surface. So if you look at this waveguide, you cannot have an electric field in this direction on the wall, because that's tangential to this side wall here. So it needs to go to 0, and this equation clearly shows that. And it also, if x is equal minus a divided by 2, you're going to get the same thing. And also you see that at x equals 0, you get to your max, which is E naught. So that's my electric field distribution over the aperture of this waveguide. And now if you leave the aperture of this waveguide open, which is the meaning of open-ended waveguide antenna, let me write it here for you. Open-ended waveguide antenna, or sometimes we call it OEW, open-ended waveguide antenna. Then you essentially gonna have an aperture through which you can radiate. Now, you can easily compare this to also microstrip antenna. This is dimension B. This was the narrow wall. So this is exactly like that. B is the narrow wall, A is the larger wall. So remember, this the polarization is actually along the narrow wall. So if I have this antenna here, it's sensitive to this electric field as the receiver. So if you want to be sensitive to this electric field, you need to rotate it 90 degrees to be sensitive to electric field in this direction. So if you now compare it to microstrip antenna, for example, assuming that this is the length of the microstrip, you had this electric field on one radiating slot, the other electric field here. So you see, you have now this electric field over the aperture. Microstrip antenna has this aperture essentially, and this aperture. So you have two aperture here, you have one aperture here, with only one difference. The size of this aperture in microstrip antenna is so tiny. This delta L is so small. We calculated that. You know that it's so small, but in the case of open-ended waveguide antenna, this is not small. You clearly see that. So in the case of waveguide, this is in the order of, for example, lambda divided by 3. This is in the order of maybe 2 lambda divided by 3. So these are not small compared to wavelengths, but this is so tiny compared to wavelength. So this is something that you can easily notice when it comes to microstrip antenna. So this is our open-ended waveguide antenna. And the other thing that we mentioned when we were in the anechoic chamber was that we have different bands for waveguide. So if you want to have your fundamental mode, then when you want to operate in a different frequency, you need to change the dimensions of your waveguide antenna. So you need to essentially have a different waveguide antenna. So let me list a couple of them so that you be familiar with a few of them. So I have a list here so that I can just repeat this. So for example, we have WR112 waveguide. It works in the so-called H band, which covers 7.05 to 10, and we're gonna have the size of 28.50 millimeter for A, and for B we're gonna have 12.60 millimeter. So that's one thing that we have here. We have also WR90. This is very famous. This was the one that was on the system when I showed it to you. That's for X-band, and it is from 8.2 to 12.4. And the size that we have, so let me write B again. These are in millimeter. So 8.2 to 12.4, this is X-band, and this is going to be 22.86 millimeter by 10.16 millimeter. And then two more, WR62. This is KU band, and this is from 12.4 to 18, and that's going to give you the dimension of 15.80 to 7.90, everything millimeter here. And then WR51, for example, that's K band, and that's going to bring us to 15 to 22 gigahertz. So let me write gigahertz here. And that's the dimension is 12.96 millimeter to 6.48 millimeter. So that's a couple of dimensions that we have. So let me tell you a couple of things here. First, the name WR. This is one reason that this WR could be attributed to is that this is, we're considering rectangular waveguide with the larger dimension A. This is B. So this is a rectangular waveguide. So WR for rectangular waveguide. And then about these 112, 90 and things like that, you can convert this to inch. And then if you convert this to inch, for example, this one, if you convert this to inch, that's going to be 1.12. So it's going to be 1.12 in this case. And now if you compare 1.12 with 112, you see why this is named like that. And for example, we could do the same thing for 22.86, and that's going to become 0.9 inches. So if it's 0.90 inches, then the name 90. So 1.12 times 100, that's going to give you 112.9 times 100, that's going to give you 90. So you see the naming structure here. The other thing that you see, as we expect, is that when the frequency goes higher, the size gets smaller here. So that's what we discussed. Or if the frequency gets smaller, it becomes bigger. So remember, when the frequency goes higher, the size becomes smaller. So you need to be very careful with fabrication accuracy, because then just a small mistake could be a big thing in wavelengths. When the frequency becomes smaller, it becomes bulkier, so it's become heavier. So if you, for example, have an antenna that needs to be moved, in the system that we have, the antenna needs to be moved. So then mechanical positioning system and things like that can be more challenging for a heavier antenna. So that's a couple of things about our open-ended waveguide antenna. So now we just gonna, and for all of them in the fundamental mode, the beauty is that it's the electric field distributions is like this. And we say E, of course, E as a function of X in this case is going to be E naught, whatever maximum we have here, cos pi X divided by A, where this is A divided by 2. This is minus A divided by 2. So this is my electric field distribution. So one thing that you immediately see here is that electric field is not uniform. In the case of patch antenna, this is almost uniform, the way that we presented it. So we said this is our electric field. So if you look at the electric field in this case, this is uniform, but here we have what we call cosine taper. So we have a taper in the field distribution, which is called cosine taper. But here we have a uniform structure. So if I want to elaborate on this a little bit, if it was uniform, it would have been like this. But then this is not possible because on this wall and this wall, this electric field needs to go to zero, and that's why we have this cosine taper situation here. So this is an introduction to this open-ended waveguide antenna, and based on this, this is going to radiate toward you, and this would be the polarization of the antenna. Now we need to figure out how we can calculate the far field pattern of this antenna. That would be our focus right now. Okay, let's start our discussion regarding calculation of the far field pattern. So to start our discussion, let me first remove the whiteboard. So this is the way that we're gonna, before talking about how we calculate that, let's see what methods we learned in this course to calculate the far field. So sometimes I give you J. So this is my electric current. So this is my electric current. If you know what is your J, then we find magnetic vector potential. And from magnetic vector potential, we can find far field E and H. So this is one way that we discussed in the course. We applied this, for example, in the case of dipoles because we know the electric current of the dipole on the wires of the dipole. Now, the other one that we saw is the magnetic current, M. So magnetic current M, and this particular one, the one that we discussed in this course, was related to a small loop antenna. So on the small loop antenna, we had the electric current that was going around the electric current in the phi hat direction. But then we said, instead of considering the electric current going in the phi hat direction, because it could create some complication for us in the calculation, we could model it by a magnetic current in the normal to the loop antenna. So this was for a small loop antenna that we consider. We essentially had an electric current on the loop, but we modeled it by a magnetic current perpendicular to the loop. And that's, we said then, if you have that, you can go to electric vector potential. And be careful about naming. This is electric current. This is A is magnetic vector potential. So it's a bit, I mean, you need to be careful. Don't confuse. This is electric current and this is magnetic vector potential. Then this is magnetic current. Then this capital F is the electric vector potential. So then you know this F, and then you can go to far field E and H. So, and then I can just write it here too. E theta becomes minus j omega A theta. E phi becomes minus j omega A phi. And we know that ER is 0. So ER is 0. And then we can find H, because we are in the far field, we can do plane wave approximation. R hat is the direction of propagation, so we have everything. Now, when you have capital F, you can do the same thing, but this time, instead of starting with E, you start with H. You say H theta is minus j omega F theta, H phi is minus j omega F phi, HR is 0. We have that. And then now you have your H, and then for E, you can do plane wave approximation again, which brings you to this. So remember, H is eta times smaller than E, E is eta times greater than H. So that was the second method that we had in this course. So if, for example, in the midterm exam, if I give you electric current, you follow this. If I give you magnetic current, you follow this path. Now for for the aperture antenna, we could use another method which can give us some insight and also can simplify our calculation. So, and I think I mean, I'll talk a little bit about insight of why I think this is important, but that's essentially our third method to calculate far field. And this is for aperture antenna, where we know the electric field distribution over the aperture. So this is essentially what I need to know. I need to know my electric field on the aperture. And usually I say electric field T, that means tangential to the aperture. For example, imagine if I have an aperture like that, the only thing I need to know is electric field tangential to this aperture. For example, this electric field would be perpendicular to this aperture. I don't need to know that. I just need to know the electric field tangential to the aperture. In fact, if you know electric field tangential to the aperture, you can always find the electric field normal to the aperture. But this is here electric field tangential to the aperture. For our waveguide antenna, that doesn't really matter, because remember, the waveguide that we consider is this waveguide, and this is TE10, and TE means electric field is transfers to the direction of propagation. That means electric field does not have any component here. So the electric field that remains is already tangential to the aperture anyway for this mode that we are considering. So this small t that sometimes you see in my notes is related to the fact that I'm assuming the only thing you need is electric field tangential to the aperture. You don't need, for example, to know this electric field over the aperture. So if you know that, then you essentially do one calculation and you calculate an auxiliary function here, which we call a small f in the notes, and or some people may refer to it as capital F, but either a small f or capital F. I think in the notes we are using a small f, and then I'm keeping a small f. So it's actually similar to here, because you see here you go from current to one auxiliary function. In this case, we call it magnetic vector potential. Here you go from magnetic current to something, and here you go from electric field over the aperture to something new, and from here you go to far field E and H. So almost identical to these three methods. So these are the three methods that most of the time we use in antenna engineering. And now we need to discuss this. We already discussed these two, and now we're going to be focusing on this, which starts with aperture. So you could start from electric current, you could start from magnetic current, you could start from electric field over the aperture of the antenna. So let's start with that and see how we can do this. And I mean, the equation that I give. If you want to study that, more, you can look at our textbook by Professor Balanis and Wiley publisher. So so now let's talk about the equations that we have for this particular case. Okay, so the first step, so we said we need to go from E tangential to an auxiliary function f. So now let's see what this step is. So f, which I have it here, is going to be equal to integral of minus infinity to plus infinity E tangential x and y e to the power of j kxx plus kyy dx dy. So now I'm also going to say where kx is k naught, or just k, that's wave number in free space, which, as you know, is 2 pi divided by lambda. So either if you put naught, you're emphasizing that you're in free space. Sine theta cos phi, and ky is k naught sine theta sine phi. So we have we have these two. So as you see, I have E over the aperture. I have E over the aperture tangential to the aperture as a function of x and y. So I'm implicitly assuming here that my aperture is in the xy plane. So this is the aperture of the antenna. And of course, you have an electric field tangential to the aperture. And for example, the one that we considering here is E naught cos pi x divided by a in the direction of y hat. So you see, E naught depends on x. So because this was my electric field, right? This is the TE10 mode. So as you move along x, your E changes. So that's the dependency on x. But because this particular mode is 1, 0, we don't have any dependency along y. So you don't see any y here. But in general, you can have a y. And remember, electric field is a vector. So in this case, this is y hat. And the function, this is the auxiliary function that we get, consequently would be a vector 2 here. So your integration is in terms of x and y. So you're integrating over the essentially area of this aperture. Dx dy would be an element of an area. And then you have this function here, j, kx here, ky. These are angle dependent. And then you integrate. And of course, if you integrate that, x and y vanishes. And then you get kx and ky f as a function of kx and ky, which is essentially f as a function of angle here in a spherical coordinate. And remember that the aperture, this integral is from minus infinity to plus infinity. So that can create some approximation for us, or maybe more accurate term would be truncation error, as we see. But essentially, ideally, you need to know the electric field over this plane from minus infinity to plus infinity. That's something that ideally you should have, which we never have this, but we're going to talk about this a little bit to see how we handle that. But essentially, later on, we turn this integration just over the physical aperture of our antenna. So that's the equation that we have. Now, if you look at this equation, what you see here is essentially Fourier transform. If you remember Fourier transform and you look at this, you see essentially two-dimensional Fourier transform. So you have a function, which is a function of x and y, and you take its Fourier transform of 2D Fourier transform to find this auxiliary function. So this is essentially the 2D Fourier transform of the field over the aperture. So that's one way of looking at this equation, that you have a 2D Fourier transform here. So this is let's now assume that we can find f. So this first step is essentially to find the Fourier transform of this function. For example, so just speaking of Fourier transform, you know that if you have a situation like this, like a pulse, then Fourier transform of this is a sinc function. So that's essentially the same thing. Imagine this was a pulse, and then on the other side, you would naturally get a sinc function. So that's our auxiliary function here. Now, let's assume that if I give you this, you can calculate this integral and get to this vector f, which is the Fourier transform. Now, if we have that, then we can find far field electric field as the following. So electric field in the far field would be, of course, as a function of r, theta, and phi, and it's going to be based on an approximation. I mean, this is. I mean, you can remove this approximation, but this is based on a approximation that's going to be equal to jk e to the power of minus jkr divided by 2 pi r. So this k is the same as this k naught. So you may want to replace it with k naught to say it's free space. So you have that. And then you get the theta hat component to be fx cos phi plus fy sine phi plus phi hat component cos theta minus fx sine phi plus fy cos phi. So let me look to that to see if it makes sense or not. First of all, usually whenever you go to far field, check for this term. So this term essentially is important. It shows that we have our spherical wavefront. And after that, we're going to have angle dependent structure. And the terms here are all angle dependent. This F has Kx and Ky that depends on the angle. So we have our angular dependency right here. The other thing that you notice here is that your electric field does not have any r hat component. Remember, if in the far field we are traveling in the r hat, and plane wave is TEM. So both electric and magnetic field is perpendicular to that. So if this is going to be your E, this is going to be your H, and this is your R hat. So E cannot have an R hat component. And as you see, we only have theta hat and phi hat in the expression. Now, you see Fx and Fy. The reason for having that is that this E is a vector. So F is also a vector, and E is tangential to the plane. So this is my plane, XY plane. So the most general form of E would be an E, for example, like that, which can be decomposed into EX and EY component. So you could have two direction, EX and EY. Subsequently, the F that you get is a vector. Therefore, it can has X component and Y component. So this subscript X, subscript Y is the X and Y component of this F. And then I have my Fx cos phi, Fy sine phi for theta hat. That's correct. And then I get phi hat cos theta minus Fx sine phi plus Fy cos phi. So that's going to be my electric field. And after that, having my electric field, I can easily write my H by plane wave equation. So now, if you look at this, you immediately realize the procedure, which is very simple, which is very similar to what we had for J and M. But here, the only main difference is that instead of going to magnetic vector potential, electric vector potential, you find the 2D Fourier transform of the electric field over the aperture by calculating this integral. Once you calculate this integral, you have this F here. And knowing this F, it could generally have two components, F in the X direction, F in the Y direction. And then you're going to have these two, and then you're going to come here and calculate your far field electric field. Again, I emphasize, this is far field electric field. In fact, the approximation used to get to this is something called method of stationary phase, and that's valid in the far field. So this is your E. When you get your E, you use plane wave because, again, you are in the far field to get to your H. So that's the framework that we have to calculate our electric field, electromagnetic field in the far field of the antenna. One thing that I could add here is that you often can simplify this. For example, let me remove this Kx and Ky from here. So imagine our open-ended waveguide antenna. This is X, this is Y, and then this is my electric field over the aperture of the open-ended waveguide antenna. Now, what you see here is that the electric field only has Y component. So electric field is something with the direction of Y hat. All of them are Y hat. So this is only Y hat component. So if it only has Y hat component, your F only gonna have Y hat component. Fx would be completely gone. And if Fx is completely gone, this is gonna go to 0 because that has Fx. This is also gonna go to 0 because that only has Fx. So you remain with this term multiplied by that, this term multiplied by that. And the beauty of this is that you immediately see that your far field electric field is related to the Fourier transform of the aperture field. For example, look at electric field, theta hat component of electric field. It's directly related. Assume that this is just y hat, so you only have this one. Electric field in the far field is directly related to Fy. What is Fy? Fourier transform of the aperture field. So that's the insight that this equation gives you. So which is very interesting that you immediately see that this electric field in the far field is related to this F, and this F is the Fourier transform of this one. So that's a big insight, because you could essentially use this to understand that if you want, for example, to have a very directive antenna in the far field, you need to have a bigger aperture. Remember, I'll go by two extreme. A very small aperture, tiny aperture. This is if you consider it, if you have a tiny aperture, it's like having nothing and then some electric field and then nothing. So from mathematical point of view, this is almost like Dirac delta function, that you have nothing, zeros, and then a tiny aperture, and then again nothing, zero. Now, what is the Fourier transform of delta Dirac function? It's essentially Fourier transform of this is essentially a DC line. So 1 all the way. So that means you get a very wide beam antenna, almost covering everything the same. Of course, we don't have a Dirac delta function because that corresponds to, I mean, almost like a point source. But that tells you that when it becomes very small in the Fourier domain, you become very wide. Now, let's do the reverse thing. Now, let's assume that you have an aperture that starts from infinity, goes to infinity, minus infinity to plus infinity. So that means you have a big aperture from minus infinity to plus infinity. So you essentially have everywhere you have electric field. So let's assume 1. Now, what would be the Fourier transform of this? Fourier transform of this would be a Dirac delta function. That means nothing, and then all of a sudden something, and again nothing. So Fourier transform of that would be Dirac delta function. That means you get an extremely directive antenna. So this ideal cases that never happens shows you that the bigger the aperture, you have a chance to have a much more directive antenna. So, and that's why that when we are not happy with the directivity of open-ended waveguide antenna, we're going to go to a different antenna, but then we're going to consider increasing the aperture. So this equation gives us insight about this, and that's why this is an important equation.